Okay, let's kick things off. We're doing a deep dive today, looking at some source material that really takes us back to the absolute basics of trigonometry.
Hmm.
As the name kind of suggests, it's all about measuring triangles. And these sources, they focus right in on the relationships between sides and angles, specifically in right-angled triangles.
That's right. It's fundamental stuff.
So our mission really is to pull out the most important ideas, the core definitions from this material, give you a clear picture.
Yeah. And even if you've seen trig before, going back to these starting points, like the source does, it sort of reminds you why it all works. It's about how angles and sides in right triangles are, well, inherently connected.
Definitely. And the sources make it super clear that step one is establishing your viewpoint, your angle of reference, they call it.
Right.
So in a right triangle, you've got that 90-degree angle, obviously,
Yeah.
but you focus on one of the other two, the acute ones.
Exactly. And the moment you choose that angle, and the source mentions, they often use Greek letters, like theta, phi, alpha.
Right, standard notation.
Then the other sides, the ones that aren't the hypotenuse, they get specific names relative to that angle you picked.
And that's interesting how the names depend on the angle.
Yeah.
So the material says the side directly across from your angle, that's the perpendicular.
Opposite.
And the one next to it, the one helping form the angle but isn't the long one, that's the base.
It's adjacent, yeah.
Yeah.
And the hypotenuse, well, that's always the hypotenuse. Opposite the right angle, longest side. Can't miss it.
Right.
The source uses a good example, like a triangle ABC, right angle at B. If you pick angle A as your reference,
Okay.
then side BC, the one across from A, that's your perpendicular. And AB next to A is the base.
But then if you switch, if you look from angle C instead.
Everything flips. Well, not the hypotenuse. But AB is opposite C, so AB becomes the perpendicular. And BC next to C is now the base. AC, the hypotenuse, stays put.
Got it. So it's all relative to that chosen acute angle.
Precisely.
Okay, so once we have that sorted sides defined by the angle the source brings in the trigonometrical ratios.
Yeah, the core idea, these are just fixed ratios between the lengths of any two sides in that triangle, and they're defined by that reference angle.
And the material lists 6 main ones. Let's see, sine, cosine, tangent.
And then they're reciprocals, cotangent, secant, and cosec.
Yeah.
Usually written sin, cos, tan, cosec, cosec.
Right, and the first 3, the main ones, using that angle A example from before, sin A is perpendicular over hypotenuse.
Correct. Ratio of those two lengths.
Cos A is base over hypotenuse, and tan A is perpendicular over base.
That's the set. And what's really key here, something the source points out, is for any specific angle, say 30 degrees, those ratios are always the same number. Doesn't matter if the triangle is tiny or huge.
Right, so they're just real numbers, no units like meters or anything.
Exactly. Pure ratios representing that angle side length.
And the source also highlights some important connections between them. Like the reciprocal ones are pretty straightforward.
Yeah, sin A is just 1 over cosec A, cos A is 1 over sec A, and tan A is 1 over cosec. They're pairs.
Makes
And there's more. Tan A can also be written as sin A divided by cos A.
Oh, right, because perc A divided by base A,
Yeah.
the hypotenuses cancel, leaving perp base.
You got it. And similarly, cos A is cos A over sin A. Shows how they all kind of relate back to sine and cosine.
Okay, this is making sense. The source had a worked example, right? Example 1.
Yeah.
With a triangle, sides 5, 12, 13.
Yeah, classic Pythagorean triple. 5 squared plus 12 squared equals 13 squared. So say AB5, BC12, hypotenuse AC13.
Okay, so if we use angle A as the reference, sin A would be perpendicular, which is BC12, over hypotenuse AC13, so 12, 13.
Okay.
Then the example flips to angle C. What's cos? Well, for angle C, the base is BC12, and hypotenuse is still AC13, so cos C is 12, 13 again.
And notice that. Sin A equals cos C.
Oh, interesting. 12, 13 for both.
Yeah, and A and C are the two acute angles, right? They have to add up to 90 degrees. They're complementary.
Right, because the angles in a triangle add to 180.
So the example immediately shows you something important the source implies. The sine of an angle is always equal to the cosine of its complement. It just falls out of the definitions.
Huh. Okay, cool. And back to angle A quickly. Tan A would be perpendicular, BC12, over base, AB5, so 125.
Exactly. The example just walks you through applying those definitions based on the chosen angle.
So wrapping this part up then, this dive into the source material really hammered home the absolute bedrock of right angle trig.
Yeah. Defining sides based on your angle.
Knowing those 6 key ratios, sin, cos, tan, and the others.
Understanding they link angles to side ratios.
And seeing those basic relationships like the reciprocals and how sin A equals cos C if A and C are complementary.
Yeah, it all flows from those initial definitions.
These ratios, they seem simple, but they're clearly the engine, that lets us connect the angles to the actual shape.
Absolutely. And think about this, building on what the source emphasizes about these ratios being constant for an angle. It means you don't actually need to measure all the sides. If you know just one side length and one acute angle in a right triangle, you can use these ratios, sine, cosine, tangent, to figure out the lengths of the other two sides without measuring them directly.
So that's the power. You can measure stuff you can't physically reach, like the height of a tree or a building.
Exactly. Just by measuring a distance on the ground and citing the angle to the top. It's all about indirect measurement, unlocked, but understanding these really fundamental trig ratios. Something to think about.